You know how it works?
I think I can figure it out.
Okay, good. Okay, so for the final talk before lunch, we have Fredrik Nordvall Forsberg from Starflight, who will talk about representing type theory and type theory with inspiration from natural numbers. Natural models.
Thank you very much for the invitation. So I like to put pictures of trees on my cover slides because I like trees and I normally talk about tree-like things. So today I'm going to talk about derivation trees, I guess. So I put a picture of the trees that are at the entrance to the computer science building here in Birmingham because they're very nice trees. So I was actually a postdoc here in Birmingham in 2013, briefly with Dan Geeka. And it was a very nice time. And I especially remember Martin had a great idea to have an AGDA club with the undergraduate students. And it was a bit of a revelation for me that you can do these really nice things even with undergraduate students. And one day I actually met Martin in this foyer over here. And he asked me if I knew anything about how to represent the syntax of type theory and type theory. Because he said that you said that you had a nice model, which I think must refer to the C-spaced model that you developed together with Shangyi. You said that, oh, I've developed the semantics, but now I don't know how to actually do the syntax, so I can prove that it is a semantics of type theory. So it would be a lie to say that I've pondered this question for 10 years, but I'm not coming back to it with this talk, at least. Some other motivation, not just to give a birthday present to Martin, is that why would you like to do type theory in type theory? Well, you could say that if you're philosophically minded, then of course, type theory, if you really believe it's a foundation of mathematics, then we should be able to do all kinds of mathematics in it, including the meta theory or type theory itself, and then we need a way to represent it, right? But it had turned out to be surprisingly hard to do this, I think, in an ergonomic way without having a lot of junk and then singling it out separately. So I'll have a small contribution towards this. And if you're more practically minded, then of course you need some representation of the syntax of type theory if you want to do meta programming in a type of proof assistant, or you want to actually formalize your meta theory or things like this. So how would you do it if you're just doing simple types? Then it's easy, because we can start by just defining the types, which are typically then inductively defined. So we're saying that the natural numbers, for example, is a type. And if I have two types, then I have a type of functions between them. That's a very non-controversial inductive definition. And then after I've done that, I can define what it means to be a context. You can see that a context is basically a list of types, given the types of the variables in my context, which is again an inductive definition. A context is either empty, or if I have a context, I can extend it with one fresh variable of a given type. And because I've already introduced what the types are, this is again straightforward, right? And after that, I can just introduce inductive again what my terms are in a given context of a given type. So for example, I can say that if I have a term of type T in this extended context, so I have one free variable of type S, well, then I have the lambda with this body should be a term of type S arrow T in the context where I bound a variable of type S, right? So again, a straightforward inductive definition because I've already introduced what the contexts are and I've introduced what the types are. These are just fixed things that exist. And then I have another inductive definition. But if you try to follow the same recipe for dependent types, then you realize that this does not work anymore, right? Why? Well, first of all, if you have dependent types, then types really only make sense in a context, right? If I claiming that fin n is a valid type, then it really depends on what n is. If n is a natural number, then fin n is probably a valid type. If n is a function, then this is not a well-formed type anymore, right? So depending on what this variable n is, I have a well-formed type or not. And of course, terms depend on types. So I can't introduce terms before the types, but I also can't introduce the types before the terms because the types also depends on the terms, right? So everything depends on everything else, basically. And we have a very dependent definition of all kinds of things depending on each other. So we have to introduce, we don't have this nice stratification we had before where we first do the types, then the context, and the terms. We have to do everything simultaneously. And we also have definitional equality, which influences what the typing judgment is. So for example, is it the case that REFL has type 2 equals 1 plus 1? Well, in order to say that this is a valid typing judgment of the term REFL, I have to compute 1 plus 1 down to 2 so that I see that the two sides are the same and that this matches the type of REFL, right? So I somehow also need to introduce these equalities into my typing judgment as I'm defining my derivations. And similarly, you naturally have substitutions occurring in your typing judgments. If you look at the application of a dependent function f to some argument a, then that should have the type of b, where we instantiate, we substitute the argument for the placeholder in this dependent function, right? So we also have substitutions in the typing rules. So we need substitutions and these reductions to somehow be part of our syntax when we formalize things, which is another source of problems. So how have people dealt with this? Well, we are looking at some formalizations in proof assistance because, of course, Martin likes formalizing things in proof assistance. So I think that the first one I found was in 1999, where it was pure type systems. It's basically just dependent types with pi types and nothing else. And their approach was to just ignore the types and then later throw out everything which is not well typed with a separate typing judgment, right? Which kind of works, but in practice means that you do a lot of lemmas and always just ruling out the impossible situations, saying that, well, it can't really be the case that the natural numbers is a function. So people tried to do this in a more structured way. So Niels Anders Danielsson, I think is the first one who did this, where we had an explicit equality relation. So, and then we proved that all constructions that we introduce actually respect this. So you could call this an early instance of setoid hell if you want, where you always have to introduce equality explicitly as just a random relation, and then you manually make sure that these things make sense. And Chapman did basically the same thing, except that he used something that's foundational, a little bit more straightforward. So Nisse used some very strange features of Agda-Lite, such as induction recursion in a strange way. And Chapman managed to just reduce this to inductive definition, which makes it a little bit more straightforward. But the setoid hell problem still remained, that we still had an explicit equality relation, and we had a lot of proof effort just to prove that things actually respected this equality relation. Right? So I would say that a breakthrough that came together with homotopy type theory was the realization that you can use a quotient inductive type to get all of these equalities basically for free, right? So quotient inductive type is like an inductive type, but you can also inductively generate equalities between things. And we can use this to force, for example, a lambda applied to a function to be equal to the body instantiated with a substitution and so on. So we just make this into real equalities in the type, which means that we don't have to prove all of these congruences that things respect this reduction relation because everything respects equality, right? And it also means that we cannot write any functions out of the syntax that actually deals with things that should be equal in different ways, which I think is a feature. It's not so good if you actually want to print these terms, for example, because you're forced to print a lambda abstraction applied to something, the same thing as the thing applied to it. But if you're only interested in normal forms, then it's fine, right? Okay, so I think that was a really, really great solution. And one way to understand it is that, so what did Thorsten and Ambrose actually do? Well, so they gave a big definition. I'm going to give you a similar big definition later. But one way to understand what this definition is that they basically took the notion of a category with families and turned it into a quotient inductive type. And a category with families is Peter Debier's notion of a model of type theory, which is somewhere between a semantic notion and a syntactic notion in a way. It's very easy to see that it corresponds to the syntax of type theory. So what are the ingredients? Well, we have a category, which we think of as the context, and the morphism of this category we think of as the substitutions between different contexts. And then we have a functor into the category of families of sets. So this is the with families part. We have a category with families. And this functor, so what is the category of families of sets? A family of sets consists of an index set, and then a family indexed by this thing. So an index set and then a family of sets. When we think of the first part of this functor, which just projects out the index set, we think of as saying for every context, we have an index set of types, right? And then indexed by these contexts and types, we have a set of terms. So we can split up this functor into two parts. One that says for every context, we have some types. And for every context, for every type, we have some terms. And then in order to make this a proper model of type theory, we also need to have a context extension operation, which says that, well, whenever you have something in the category, and whenever you have a type over this, then you can turn it back into the context again, which is modeling the context extension operation. Right? And this has a universal property, which tells you what morphisms into these things are. And in particular, if you spell this out in concrete terms, so rather than saying you have a category, say, well, you have a sort of objects, so you have a sort of morphism, so you have an identity morphism, and so on. Then you see that this is a generalized algebraic theory, and we know by general reason that these things, generalized algebraic theories always have initial objects, right? So in principle, it should be possible to do this. But of course, this result works in some kind of meta theory, which is maybe extensional type theory or informal set theory or something like this. So it's not completely trivial to take this result and just turn it into type theory, right? Which is one of the contributions by Ambush and Thorsten. So one problem, if you try to do this, is that you look at the equations that you have for your categorical families, and then you have things like functors should preserve identities, which, so what's the functor part of these functors into fum sets? That corresponds to the action of the substitutions, because we're thinking of the morphisms as substitutions. And we're saying that if we have a substitution and a type, we get another type. So in particular, these functors should preserve identities. So we should have that if I have a type A and I substitute with identity substitution, well, then that should not do anything, right? I'm just replacing X with X everywhere, I get the same thing. So that's one of the equations we have. And we also have the corresponding equation for terms. We have a term T and an identity substitution. Applying it should not do anything. But we notice that this equation here is only well typed because we had the previous equation, right? So little t here is a term of type A, say, and after I apply the identity substitution to it, then it's the term of type A where I have applied the same identity substitution, which is okay because I had this previous equation. But if I didn't have that, then I would be in trouble. And if I do this in type theory as a quotient inductive type, then I have to explicitly transport along this equation to fix up the types. I have two things of the same thing, right? So if I do this as a quit, I get something like this rather than just that. I say that, well, if I transport this term along that, then I get T, of the right type. And unfortunately, if you do this in cubical agda, if you want to formalize this, then cubical agda will complain and say that, well, you have some weird function in the middle of your inductive definition. This is not obviously strictly positive, and I don't know if this is safe, right? Which is bad news if you actually want to check things with cubical agda. Of course, so just before this, I edited out the slides to say, yes, Thorsten, you can use path P, but then you didn't ask any questions in the first half, so I didn't dare to keep this. So yes, Thorsten, you could use path P, but then you're just doing cubical agda rather than, say, translating this GAT into type theory, right? But yes, you could do that, and I think it works in many cases. I'm not sure if it works in all the cases. So here it works because you just have a transport on the outside, right, rather than somewhere deep inside the term. So that would be another solution. But I'm going to try to show you another one, and I'm not sure which one is best in practice, but I think it's worthwhile to try both. So why do we need this transport? Well, in general, we need it because we are really trying to be precise in the types of our subterms, right? So for example, we have this extension of a substitution. So if I have a substitution from gamma to delta, and I want to make a substitution into a context where I have one more variable, then saying that I first have a substitution to the first part of the context, and then I have to give a term of this last variable. That's how I make a substitution into a non-empty context, right? You have to give a term for each thing I want to substitute into. But then I'm insisting that this term I have here really has the type A where I have applied these substitutions so that it matches up overall, right? So we're really insisting that we have this specific type here, and that's where the transports come in, because we're insisting on a specific type. So we could ask for something equivalent. So rather than saying, using this here directly, I say, I want any B, I take any B you want, as long as it's equal to the one I really want, right? According to the Henry Ford principle, any B, as long as it's equal to the one I really want. And we know by contractibility of singletons that these two types are equivalent in homotopy type theory, so I'm not really changing anything, except that I'm changing the definitional behavior, right? In the sense that before I had to have a transport here when I used this term, but now the transport disappears and I'm just keeping the same equality proof somewhere else, which makes cubical Agda happier because there's no strange transport function in the middle of my inductive definition. But if I do this everywhere, then there's really no need to keep these B's around anymore, right? I can just strip them all out, and then I can reintroduce them at the end with a function which says for every term, what is the type of this term, what it should be. Right? So then we end up with something like this instead, where before terms were also indexed by types, but now we just strip that out, and we reintroduce a function which says for every term what the type is, right? But we keep everything else the same. And I'm not going to show it on the slides, but I'm going to set truncate all of these things. But just like when you do categories in HOT, there's actually no need to set truncate the objects of the underlying category. But it will turn out the syntax that this will be a set anyway. And if you stare at this a little bit, you see that it looks quite similar to what Steve Odie and Marcello Fiore calls, well, Steve Odie calls natural model of type theory. We basically reformulate the notion of category with families and turn it from the index perspective to the fiber perspective instead. With this pre-sheaf here, or a natural transformation between pre-sheaves. Okay, so here is the whole calculus, I think, unless I forgot something. And I've highlighted the things that are actually different in this formulation, because it's far too much on one slide just before lunch. So let me just talk through the things that are different. So first of all, we have this type of constraint here in the extension, rather than using the A explicitly. And before we halfway through, we said B was equal to this. We just turned that into saying that the type of this term should be the thing we really want, right? And because we have removed the types in the terms, we actually simplify these equations. They don't have to have these transports anymore to fix things up, because these things have just gone away. Another small thing we do is that sometimes when you have an equation which you can derive from other things, so for example, you have this kind of equation and you want to know that the right-hand side has the same type as the left-hand side and it's derivable from some other things, then if you try to put this derived proof directly into the definition again, then cubical Agda will once again complain, right? So what we do instead is we just ask for any proof of the equation we want, and we know that there is a proof. And because we set truncate things, we know that all of these proofs will be propositionally equal anyway. So we are asking for one element of a contractible type, which gets us around the strict positivity restrictions of cubical Agda, which is a bit annoying, but it works. And similarly here, when we have this beta rule for the second projection, then we really want to say what is the type of this, and we just ask for this extra thing rather than, again, deriving it from smaller pieces. Okay, and then we can do the same thing for the other type formers, and it works quite well, I think. So we did pi types, Booleans as a representative inductive type, and a universe. And in the same way, sometimes it's helpful to introduce these kind of spurious, superfluous tie-off proofs, where again, we know we can derive them from other things, but then later we can just instantiate them with anything we want. Okay, and then as expected, we can use pattern matching on this kit to actually define the elimination principle, which then shows that we have the initial such model. Except annoyingly, it doesn't quite work. It would be really nice if it did, but we have to mark this as terminating for some reason. I think it's because we want to have this kind of preservation of tie of, saying that tie of the recursive call should be the recursive call of the tie of. But because we factor these things out as equations like this, it's very convenient to also factor it out like this. But then here, in this type, you suddenly have the recursion operator applied to some random type B in the middle of your recursion, which would go away if you just inline this here. But yeah, so it's a bit annoying. But morally, we're always applying this thing on structurally smaller things. So in practice, it computes and works. And surprisingly, I thought we had this kind of unnecessary definitions in our inductive definition. I thought, okay, when we give them all, when we define the recursion principle, we should just define these for the users, and they shouldn't have to worry about these things. But it turned out that it's actually good to let the users define these things themselves, because sometimes you can give a more direct proof of something. For example, that's not reducing away if you use the derived notion. And I think this is related to the fact that in cubical lambda you don't have so-called regularity. So transport of a REFL does not compute away. So sometimes the derived notion will turn out to be transport of REFL, but you can just give REFL directly instead. So it's actually also good for users to keep this around. So here's one example of a model. It's the standard set model, where in order for these things, for types and so on to be really set truncated, we locally assume uniqueness of identity proofs. It should be okay cubical without glue, because we're not actually using univalence. And the thing I want to point out here is that when you construct this model, you're kind of forced to go back to the index perspective in secret, right? So saying that the terms in context gamma, well, it's going to be the sum over all possible types here, and then a term of that type again. And then the pi of is just the first projection. So I don't know of a clever way to actually define this in a fibered way. And of course, you can also do the term model if you want, where everything is just the same, right? And then we tried some things to see if this actually works in practice, because of course, anyone can define an inductive definition. And some things work, some things don't work so well. So normalization by evaluation was surprisingly easy to do. Maybe in part because this was done by our research assistant, who actually knows what they're doing. But it was nice to see that it just works, because there are no transports anywhere in these things, and it just computes, so you can actually run things and get a normal form. We also tried to do the logical predicates model, where you, as a model construction, so you take a model and you want to construct the model of logical predicates over this model, but then the types sneak into the context, because you want to say that a new type is a type in an extended context. It becomes like a predicate, right? It's a type with one more free variable. And then all of the transports turn into equations between contexts, and you get the same transport as before. So this did not work so well, and it was not really a win to do it this way, I think. We also tried to do strictification, which also worked very nicely in this way, but it doesn't actually solve this problem, because we can't strictify all of the models. We can turn some of the equations into things that can be proven by REFL, but it doesn't work for all of the type structure, for example. So it doesn't solve the logical predicate model. So it's somewhere between a happy result and a not happy result. Okay, I think it's well time we stopped. So let me just summarize what we did. We tried to define a new notion of, or a new representation of the syntax of type theory, which kind of in hindsight can be seen to be inspired by natural models, which the good news is that it lists fewer transports in the definition, which makes some things easier. But the bad news is that these transports somehow come in when you actually work with these things, and there's no free lunch, I guess. And of course, the real reason why we're interested in doing this was that the definitional principle we used to define this, where you define something inductively with quotients, and you also have a recursive function, which is targeting the same thing you're defining, is a very strange thing. And we want to see if there is a good use case for these kind of definitions, so that we can study them further. And if you want to see the formalization, it's on GitHub. If you want to see the paper, this is secretly a link. And that's it. Thank you.
It's the mic. Folks online.
Thanks for that. Oh, I'm so loud. I had an idea. I don't know if it will work better or not. It might be strictly worse than what you've done. But another way to get around the transport positivity problem might be just to add a constructor for the conversion rule that takes an identification as its argument, and then a higher constructor that says that this thing does the right thing on reflexivity. And then, well, the J principle allows you to eliminate these so that, it disappears, but you could use the constructor inside the depth. I don't know if it will work, but have you thought about this?
Like communication by telegraph, yeah. No, I have not thought about that. That's an interesting suggestion. Maybe we should think more about it. Thank you.
Thanks. So this was a very nice way of avoiding transports. I know because I played with this with Chuanji kind of 10 years ago. Can you say, you said at some point that this is similar, but not exactly the same as Fiores and now with this thing. Can you say what the difference is?
Basically, I didn't want to claim too much. I think in some sense it's exactly the same because their thing is equivalent to the normal notion of categories with families. But the thing I had in mind was that we are using their notion of a natural transformation between pre-sheaves to encode the type structure. But we are keeping the same notion of context extension directly from the category with families. We're not directly phrasing that as universal property of a representable natural transformation. Right.
In the interest of time, let's take further questions over lunch. Let's think. But again.